Get started with our first session of the afternoon. I'm very happy to introduce Jonathan King, co-founder and chief scientist at Atom Computing. We'll be talking about their work on logical qubits.
Cool. Great, thank you. Probably could show more results than I have time for, so I'm going to try to keep it to a subset of stuff that will be interesting here. So just if you don't know, Atom Computing is a company working on neutral atom qubits, gate-based machines. We're based out of actually several places now. We have an office in West Berkeley. You can almost see us here. That's sort of the cluster of our error correction, applications theory type people. Most of our, or I guess all of our quantum hardware is based out of Boulder, which you can kind of see on the right there. And we actually have offices in Austin too, a small one, and just recently opened one up in Copenhagen, Denmark. Cool. So I'm just going to jump right into it since we don't have a whole lot of time here. I'm not going to make this a talk about the physics of neutral atom quantum computers. If you have questions, happy to get into that. This is really going to be about things we've done with them, kind of at the level of circuits and error correction. So pretty much all the physics you're going to see, the atomic physics you're going to see is on this slide and the next one. 2 slides. So what we have is a bunch of neutral atoms trapped by optical tweezers or trapped by light in a grid. We move them to an interaction zone, which is labeled here, IZ. Everything is done with laser light. So when you want to have atoms do 2 qubit gates, you move them here so they're physically next to each other. You do a 2 qubit gate using Rydberg interactions, then they move back to wherever you want them. You can do single qubit gates locally. So we essentially have an all-to-all connectivity, universal gate set at the physical level. Read out, you do state preparation, everything is done through lasers optically. We've developed techniques. We have some papers out talking about how we do non-destructive measurement. So you can read out the atom state without blowing the qubit away. You can, read out if it's a 0, if it's a 1, or also if it has been lost. So it's important to remember that atoms, they don't live forever. They can get hit by a stray molecule or stray atom of gas, or they can be lost for other reasons too. Everything we're doing is building towards a universal error-corrected gate-based quantum computer. Maybe I'll skip over energy levels and do a simple diagram. Just as a reminder, since it seems like there's a lot of familiarity with some analog quantum simulators here, here's what's different. Everything's gate-based, and our 0s and our 1 states are the nuclear spin states of the ground electronic state. So if you're used to thinking the 0 is ground and the 1 is Rydberg, that's not what we're doing here. We use the Rydberg, which is the R there, transiently to make couplings happen between atoms, but we don't actually use that as one of the computational states. Happy to answer any atomic physics questions later, but I would really kind of want to just get into what have we actually shown in our recent papers. So as of almost a year ago, this is the architecture that we're using for this paper, which you can find at that archive length. So we can obviously load a lot of atoms in there, much more than this, but for these circuit results, basically, we made a 256 qubit arrangement, 16 by 16. There's 8 interaction sites. Sorry, I'll use the cursor so people online can see it. 8 interaction pairs here, where atoms would be moved by optical tweezers up into these sites. They're physically close enough to each other that the Rydberg interactions can do 2 qubit gates. You can do all 8 pairs at a time, so there's some parallelism there. There's also a certain amount of parallelism in terms of which atoms you can move at one time and what 2 qubit gates you can do at one time. Some sort of, let's just say, performance characterization of what the machine was at this point in time a year ago. Basically, 2 qubit gate errors that are on the order of, this is probably the right number to look at, on the order of 0.5% within the qubit subspace under realistic circuit conditions where atoms are moving around a lot. There's also like a 0.75% sort of probability of losing an atom, which goes away. So those 2 things added together are essentially the total gate error associated with 2 qubit gates. All right, this is the machine we're working with. I blew by that in like a minute and a half, and the rest is just going to be about what have we actually done with it.
Can I just ask about moving errors? Like what kind of errors introduced by moves? So how you're characterizing those? And how much do you have of those?
Yeah, to be honest, I don't remember. I don't have the number ready to go off the top of my head about how much loss happens just from the movement itself.
Well, not loss, like just kind of leaps and decoherence and.
Oh yeah, there's Yeah, I guess I would say, I don't have, maybe have the number ready to give you, but the dominant source of error that happens during movements would be like dephasing, dephasing of the atoms just from fluctuating frequencies. That's something on my very last slide, the statement will be there that future improvements have to do with things like decoupling and echoing.
Are all 256 qubits taking part in the computation?
I have one slide where I'm going to show a circuit that uses all of them. So I'm gonna not assume that everyone here knows the details of error correction. So I'm gonna do like very, very simple. If you're an error correction expert, you can probably just zone out during the slide. Here's a really simple code, 422. What these numbers mean is 4 physical qubits to encode 2 logical qubits. It's also the smallest instance of a toric code. A toric code is the surface code essentially that's on a torus instead of just a surface with edges. The final 2 of the 422 means it's distance 2, which is basically how far away the code words are from each other. So you would need to like basically flip 2 qubits to take it from one code state to another. So it can detect any single qubit error in the qubit subspace. I'll tell you what that, and it can correct any erasure. And if that's confusing, I'll just explain what that means. Imagine, all right, let me point out what I wrote down here. These are the 4 possible states. There's 2 logical qubits encoded here, so there's 4 basis states. Here's what they are in terms of the actual like wave functions of the 4 physical qubits. Imagine if you just read out your logical qubit and this is the 4 physical qubit set. That's none of these. There's no state down here that would actually ever give you that result. So you know an error has occurred because it's not any of your code states. But you don't know what has occurred. That's easy to see. Like it could be this one. The first qubit could have flipped and given you that result. It could also be this one. The last qubit could have flipped, giving you that result. So, you're distance 1 away from both of those. So a distance 2 code actually can't correct for a single error because it's equal distance away from both states. You don't know which one's closer. Imagine if you had an L for loss, like one of those qubits just physically disappeared. There's actually only a single state up here that is consistent with that, if you assume that only one error has occurred, and it's this one here. So that's what I mean when I say a kind of Pauli error in the qubit subspace, detect, correct. If it's an erasure, you can imagine if that qubit was lost, actually I'm going to show you my next slide here. If that qubit was lost and you did some syndrome extraction, which I haven't explained to you yet, to identify that's the one that was lost, you could actually replace it with a new qubit, reinitialize it, and keep going with your computation. And you would actually be able to correct it. So
why the loss? You can't lose a 1?
There's only one state up here where the final 3 qubits are.
Oh, okay, fine.
Because there's actually 2 bits of information or 2 pieces of information.
Yeah, I get you.
You know which qubit was lost. In this case, you know that an error occurred, but nothing tells you which qubit it happened on. Imagine several different cases. So I'm going to show you a kind of a set of demos that we did where I think it's the first 2 or 3 things I'm going to show you. It was all set up this way. We use these 422 codes. And for some of them, we use 412 codes. By the way, that's just the same thing, but you can ignore one of the qubits as a gauge degree of freedom. And you can run circuits on them. And for all of these in the first half of the talk, you're not doing mid-circuit measurement or syndrome extraction or any of this stuff yet. You're just running an algorithm on these circuits, reading it all out at the end, and decoding in just kind of the way I explained on the last slide. So a CAT state, which is the same as a GHC state, just a maximally entangled state on 24 qubits. You could write that circuit in this way if you just forget about error correction for now. There's 24 qubits here to make this state. Encoding that 24 qubits into these 422 codes requires this many physical qubits. And this is the actual physical circuit that we ran. So the idea here is just to make a large entangled state out of logical qubits rather than physical qubits. There's some details here about, you might, if you're paying attention, see these extra little qubits there. These are like flag qubits that will let you know when a state preparation error happened at the logical level. So you can throw away those data, do some post-selection. There's a little bit going on here, but basically, if you ask yourself, like, what is a test that would allow you to say this genuine, like, multipartite entanglement between all your qubits? And you would say that, I guess, in order to be consistent with that statement, the sum of the errors where you measure all the qubits in the X basis with the errors in the Z basis together would have to be less than 50%. Otherwise, there's no other single state that can give rise to those statistics other than one that's genuinely entangled between all qubits. So when we say unencoded, it means we just ran the circuit on physical qubits with no 422 codes, no error correction or anything. Got these error rates, the sum of which was 42%. And then we can do what I just described, encoding them into these 422 codes. Really what I'm doing is comparing this circuit on the left, this circuit on the right. So it's physical versus logical encoded qubits. And the sum of the errors is in fact lower. I can go a little further and do some more post selection and say, how about I just throw away, instead of like trying to correct these loss errors, how about instead I throw away the data? And then of course the error rate gets lower, but what goes along with that is acceptance rate. In this case, I'm sort of constrained. I can only accept a little bit less than 1% of the data without post selecting it. Whereas if I do the correction, I get to retain 6 times as much data. And there's actually a sliding scale here of like, if I include all the data, the error rate, like 30%. If I constrain it to not have any loss of any atoms in the entire circuit, the error rate gets down to 10%, but I pay a price, which is essentially like what fraction of my shots, fraction of my bit strings do I have to throw away? I'll point out, like, I'm not actually describing how a large scale like quantum computer is like going to run in a useful way. Because you actually don't want to throw away shots. And you can see that, as this scales up, if the number of shots you have to throw away gets bigger and bigger and bigger, eventually you're retaining no data. This is really just a proof of a principle of the statement that at the level of an error correction code, loss, or really erasure, because you convert loss to erasure, which I'll talk about later, is an easier error to deal with. And then so as you scale up to bigger error correction codes that have higher distance, and then you're doing mid-circuit measurement and replacing qubits, then you actually will be correcting rather than post-selecting these kinds of data. So this is just a proof of principle to show how loss to erasure conversion is a tool that makes performance higher. This is essentially the same kind of thing. It's just a different circuit. The Bernstein-Vazirani algorithm is fairly well known. It's basically like there's a hidden bit string. In theory, like if you have a oracle that gives you just basically the dot product between some vector or some bit string and this hidden bit string, classically, try every possibility to get something out. In the quantum case, you can do it sort of in a single shot. I'm not going to dive into details here. I just kind of want to give you a sense of the scale of what we ran here. You can see that it's like 112 physical qubits. You can see how big the circuit is. And sort of this interesting thing, like the error rate was unambiguously lower for the error corrected or error detected qubits. If you actually think about the Bernstein-Vazirani algorithm, it's a question about how many times do you need to query the oracle in order to get your answer. And there's some ambiguity here. Well, like if you actually have to post-select data, then you're not actually guaranteed to get a shot back each time. I would say if we really want to talk about, let's say the computer science here, there's some ambiguity as to actually which one of these is a better algorithm, encoded versus not encoded. Practically, that's not what this talk is about. It's about just showing, can we do error correction codes? You can see that it works here. One more conceptual thing. We're already about almost 15 minutes in. So again, we haven't done any mid-circuit measurement yet. I'll get to that in like 2 slides. But basically, here's a little snippet of a circuit for how you would do syndrome extraction mid-circuit. So instead of just measuring things at the end of the circuit, I would want to actually run a little circuit like this to basically get the product of all the Z measurements stored in an ancilla qubit. That's kind of a standard thing you do in error correction. Here's like a version that actually gets both the X and the Z kind of syndrome measurements onto these 2 ancilla qubits. But the interesting thing is you can sort of recompile it and just like swap some definitions of qubits around. And so you can run the same sort of syndrome extraction here, except for what actually happens is that now you've actually swapped the identity of the ancilla qubits and 2 of the data qubits. I'm not sure if that's really easy for you to see on this slide. It'll be easier to see on the next slide. But the point is, and the reason there's a couple other citations here, the point is that, you know, in neutral atom systems, for us and for others, atom loss is an intrinsic part of the error mechanism. The fact that a lot of our gate errors turn into atom loss is actually something we can take advantage of for reasons I was just describing, which is that loss is an easier error to deal with error correction codes. But there's this tricky thing is that if you're losing qubits during your computation, you need to replace them somehow. So I think this will be a little easier here. But now when you see this thing stacked up into a repeated syndrome extraction circuit, here's the 4 qubits in the 422 code that we've just been talking about. You know, you do some kind of operation on them. Here it's a you know, a gate between the logical qubits in the block. You take these ancilla qubits here, do these gates, they actually get swapped in. And then you see over here, these lines actually have ended and those can be measured. And now those are the ancilla qubits. So like at the beginning, these top 2 lines here were data qubits, but they end the circuit as ancilla qubits. Oops, went too fast. And then these new ancilla qubits have taken over. And this process repeatedly will, you know, every time you do the circuit on the screen, you've actually replaced all the qubits in your circuit. In this first paper from last year, you know, we weren't doing mid-circuit measurement, so we were just consuming new qubits every time we did this. What we show here is running these circuits. These circuits are kind of written in a funny way. These are logical circuits on the 2 logical qubits in a block of the 422 code, and showing how the error rates increase, and showing how the error rates in the error corrected or error detected versions are lower than if you'd run it on physical qubits. But the point is here, you can just keep refreshing your atoms. You can tell I'm running a little, I'm going to be running out of time if I don't move quickly. I'm not going to talk about the details here because I think it'll be a little tough. But somebody asked, like, did we use all the atoms? Yes, we did. Here's a code, the 1664 code. So if you do 16 blocks of this, you use all 256 physical qubits. 6 times 16 gives you 96 logical qubits. This is just a state preparation circuit. It's a circuit that like creates them all into actually the alternating +0, +0, +0 states for these 6 qubits. And we ran 2 versions of it. One that has a sort of fault tolerant flag step, which allows us to flag errors to post select out. One where we didn't do that. The kind of thing here is to note that, maybe if I click the next one, no, sorry. We get a lower error rate if we use the flagged version. This is 0.53% versus 3.98%. But again, you have to throw away some of your blocks of because you're post-selecting. So actually, if you look at this little thing right here, with some non-zero fraction of the time, we correctly prepared all 16 blocks, which is, just to coalesce that into one statement, it's that at least some non-zero percent of the time, non-zero fraction of the time, we were able to prepare 96 logical qubits to the correct state using all 256 atoms. This machine. Cool. So I went kind of fast with this stuff and I've already used almost 20 minutes. Here's the more recent stuff, which I think is more interesting. So nothing I've done showed so far has showed mid-circuit measurement or refilling atoms or reusing qubits. That's what we did a machine upgrade for. This is sort of that architecture I showed earlier, except for we've added a few things. In addition to the green spots where 2-qubit gates happen, we've added a place where mid-circuit measurement happens. MZ is our code for measurement zone. There's also a reservoir here. These are just extra atoms. So if you're running a circuit, and you measure a qubit, you get a 0 or a 1, or you get a loss. If it's a loss, then a new atom is immediately pulled from this reservoir and put where it is in the middle of the circuit. So we get that information about whether the atom was lost, and we actually refill it fast enough to keep going with the rest of the circuit. There's some details here about like some physics we showed in the past that wasn't good enough to use in this context. So this was kind of the big deal earlier this year that we got the machine. the state where all of these pieces were integrated together. Here's a cool picture of a particular circuit running. Mostly what you can see here is the atoms moving back and forth from the what we call the register down here to the 2 qubit gate spots in the interaction zone above. So this is a repetition code. It's not a fully quantum error correction code for those who know about these things. It's actually a classical error correction code. So you can choose it, like basically the way you can set it up is to just correct either bit flips or correct phase errors. It doesn't do both at the same time. So the point here is really just to exercise all the machinery that we put together. In addition to just being able to run circuits, detecting loss, doing mid-circuit measurement, and doing atom refilling. So this is a circuit here, and each round looks like this, or rather this is, I guess each round looks like this, where there's like a set of 3 mid-circuit measurements here, a set of 3 mid-circuit measurements here, and it's doing that same trick I explained earlier, although I think it'll be hard to see here if you don't know what you're looking at, where the data and ancilla qubits are swapping at each step. And every time one of these measurements is done, if the atom is missing, a new atom is brought in there, and it is replaced and initialized, and then the circuit keeps running. And yeah, so the sliding quantum information is just what I was saying about swapping. So it's kind of one of these Barber's pole kind of thing. There's another name for it. I forget what the kind of name for that phenomenon is, but basically just kind of keeps sliding down. When we wrote up here toric repetition code, it's because it's actually a repetition code where the ends are sort of connected to each other to enable this. Oh yeah, so I wrote the phrase delayed loss to erasure conversion here. So, you know, loss itself is, you know, not actually converted to a detectable error or used as a detectable error until you've actually measured it. So you have a measurement here, and at this point you will know if loss has happened, but the loss could have happened any point in time before that since the last measurement on that qubit. So that's this idea of delayed erasure conversion. You know, the best information to have would be to know exactly at what point in the circuit it was lost. But you actually only get a window, you know, somewhere lost in that window, which is less good, but it is still good. But let me show you results. Detector frequency basically is a measure of how often let's say a bit you measure is different than the bit you measured in the previous round, which is something that you expect not to happen because if there are no errors, these measurements would be the same every round. So this is kind of a measure for like the physical error rate happening during the circuit. These sort of logical errors are basically after decoding. How does the error go down? And I don't know how well you can see, but there's a suppression of error. We've done, I mean, what phase sensitive and phase insensitive are probably a little beyond the scope of this talk. But there's a suppression of error kind of down to, it's a little not clear if it's hitting a noise or hitting a floor or if just the statistics. Therefore, the error bars are such at a point it's hard to track it as it goes down to really low error rates. The x-axis here is distance, which is basically how big the error correction code is, how many physical qubits you use to encode a single logical qubit. So the higher distance or redundancy you have, or if you remember the discussion I had on the earlier slide, the distance is a measure of how far the logical 0 state is from the logical 1 state. So more errors would have to happen to sort of get you from one to the other. And so sort of the hallmark of error correction working is that as you increase the distance, the logical error rate goes down. So this is, yeah, it's not a quantum error correction code because you need to correct both bit flip and phase errors, but this is a type of error correction code that makes use of all these, features I just showed of mid-circuit measurement, loss detection, atom refilling, and so there's kind of it can just keep going forever, you know. Eventually you will build up so many errors, your information is no longer there, but there's like no fundamental, let's say, hardware limitation that prevents the circuit. You just go. One more thing, I think I'm just about done. I know we're going to do questions soon. Also using this machinery, oh yeah, here's one more thing I haven't shown, which is classical branching and feedback during circuits. This circuit, RUS, means repeat until success. This is just preparing a Bell state in code to these 422 codes. And so if you don't follow the full circuit, that's fine, but there's some mid-circuit measurement. There's actually some classical logic that is decoding logical qubit measurements for these two qubits are in the correct state or not. If they're not in the correct state, then you repeat success. And at which point you just read out the logical qubits you care about, see if they're in a Bell state. And you see that some fraction of the time you get it on the first step. And if you do it more than 10 times, you've essentially, with nearly 100% probability, gotten the state you want. So this is similar to things like, let's say, magic state distillation that you would need to actually make quantum computing work at utility scale. But yeah, this is the last slide. So demonstrated logical circuits on a neutral atom system, shown loss to erasure conversion and how that actually helps at the logical performance level. We've shown repeated error correction, mid-circuit measurement, qubit reloading, and classical logic. And yeah, the outlook for this is basically just keep pushing on performance, making things better. I mentioned things like dynamical decoupling and echoing to work on these physical error sources and just keep going ahead. That's my last slide. Happy to answer any questions.